Dear students, software testing methodologies, public question paper, video 5. That is public questions, model questions from unit 5. That is the important questions from unit 5. Dear students, is software testing methodologies, unit 5 and video 2. Unit 5 and video 2. Continuation of state graphs and transition testing. Good and bad state graphs. What is meant by good and bad state graphs? Good and bad state graphs. What is meant by good state graph? A state graph is said to be good when every state, input, transition, and output is specified clearly and specified by understanding. So if state, input, transition, and output all are specified clearly and understandable, then it is called as a state graph, is a good state graph. Here the sequence of inputs is specified for every state that results correct output, because here what it contains, the sequence of inputs, it contains about the sequence of inputs, and these sequence of inputs are specified for every state that results correct output. In good state graph, there is exactly one transition specified for every state and input combination. Remember, in good state graph, there is exactly one transition specified for every state and input combination. So the transition bugs may not occur because we are specifying one transition for every state. So because of that reason, the transition bugs may not be occur. In good state graph, only one output action is specified for every transition. One more thing is, in good state graph, only one output action is specified for every transition that results to an appropriate state graph. That gives about the appropriate state graph, because only one output action is specified for every transition means it gives about a appropriate state graph. In good state graph, the bugs are less and easy to identify. One more point is, in good state graphs, the bugs are less and also easy to identify. Now, what is meant by bad state graph? A state graph is said to be bad when every state, input, transition, and output is not specified clearly and difficult to understand. Quite opposite to good state graph. Quite opposite to good state graph. Bad state graph means it is quite opposite to good state graph. That means a state graph is said to be bad state graph when every state, input, transition, and output is not specified clearly, and also it is difficult to understand. In bad state graph, there is no sequence of inputs specified that results incorrect outputs. One more thing is, in bad state graph, there is no sequence of inputs specified. There is no sequence of inputs specified that results incorrect outputs. In bad state graph, there may be either none or more than one transition specified for every state and input combination. Previously, in good state graph, there is only one transition, but here there may be either none or more than one transition specified for every state and input combination. So finally, what we can say, previously in good state graph, there is the transition bugs may not be occurred, but here there is more than one transition or there is a none of the transition, then we are having about the transition bugs. That means transition bugs will be occurred. In bad state graph, there may be none or more than one output action specified. Okay, so what is meant by this? In bad state graphs, there may be none or more than one output action specified for every transition. None or more than one output action specified for every transition. That results to an inappropriate state graph. It is about the previously it is appropriate state graph, but here it is inappropriate state graph. In bad state graph, the bugs are more and difficult to identify. In bad state graphs, the bugs are more. The bugs will be more and will be difficult to identify. Difficult to identify. In testing, we deal with a good state graph and also with a bad one. In testing, we deal with a good state graph and also a bad one. The following figure shows examples of improper or bad state graphs. See here, the first one, A state and B state. So A to B, there is a transition. One is nothing but self transition. Then 2 is next transition. Next self transition. That may be 1, 2. Again, how we can write the same transition here at B? So in state B, the initial state can never be entered again. What is meant by 1? 1 is nothing but the initial state. This is A. This is in state B, the initial state. The initial state can never enter again. Okay, 1, 2. 1 is there. Again, 1 is not possible. Okay, so that's why it gives about the bad state graph. In second figure, A comes under the 1. Okay. From A to B, there is 2. Okay. Again, from B to A, 1, 2. Okay. But from B, it is 1, 2. Anyhow, how we can reach about the C? Cannot be entered. C cannot be entered because from B to C, there is no. That is the main here problem. So there is no way to go to C from B. So therefore, C cannot be entered. That is a problem. Now here, next one, A consists of 1, 2, B consists of 1, 2. But there is a reach from state A to state B, there is no reachable. From state A to state B is not reachable. From A to B is not reachable. That is the problem here. Here it is A, it consists of 1 transition. Here it is consists of 1. No transition is specified for input of 2 when in state B. Here from A to B it is 2. Okay, no transition is specified for an input of 2 when in state B. Okay, in state B again you are writing 1. That is the problem. Here there are 2 transitions specified for output of 1. So 1 contains okay, there are 2 transitions are specified. So this is also the problem. Okay, 2 transitions specified for an input of 1 in state A. Okay, 2 transitions. Here it is 1. Here it is 1. So 2 transitions specified for input of 1 in state A. That is the problem. Okay, that is the problem. Now, state bugs. Second one. What are the different state bugs? What are the different transition bugs? What are the different output errors? First one, we see about what is meant by state bugs. What is meant by state bugs? The bugs in states are called state bugs. Simple. The bugs in states are called state bugs. The state bugs arise due to the following reasons. The state bugs arise due to the following reasons. Number 1, number of states. Number 1 reason is number of states. A state graph consists of number of states. State table is used to record number of states of the state graph. So, to record number of states of the state graph, what we're going to be used? We're going to be used about the state table. In state table, if number of states is not recorded or if number of states are missed, then the result gives the state bugs. Okay, the results gives about the state graph. So number of states means a state graph consists of number of states. So state table is used to record the number of states of the state graph. In state graphs, if number of states is not recorded, or in state graph, if number of states are missed, then the result gives the state box. The result gives the state box. Next, to find the missing states, first find the number of states. To find the missing states, first find the number of states. First find the number of states. The number of states is founded by as follows. The number of states is founded by as follows. Identify all the component factors of the state. All the component factors of the state. Then identify all the allowable values for each component factor. Allowable values. Now the number of states is product of the component factors and allowable values. Component factors and allowable values. Functional specifications are used to find the component factors of the state. Here, functional specifications are used to find the component factors of the state. Functional specifications may also be used to find the number of possible values for each component factor. Functional specifications may also be used to find the number of possible values for each component factor. Second one, impossible states. A state that is not possible is called impossible states. A state that is not possible is called impossible states. For example, a broken engine cannot run. So running a broken engine state is called impossible state. Okay, because broken engine cannot be run. So running a broken engine state is called impossible state. There are some combination of factors. That appear to be impossible. They are gear. One is called rear gear, N neutral gear, first gear, second gear, third gear, fourth gear. How many factors are there? Totally 6 factors. Direction, forward, reverse, stop. 3 factors are there. Engine, running engine, stopped engine. 2 factors are there. Transmission, okay, transmission is okay. Transmission is broken. 2 factors are there. Engine is okay, broken. That equal to 2 factors are there. So for total, this gear, direction, engine for a engine, total equal to 6 into 3 into 2 into 2 into 2, that equal to 144 states. A broken engine cannot run. So the combination of factors for engine condition and engine operation is 3 factors only. A broken engine cannot run. Yes or no? A broken engine cannot run. So the combination of factors for engine condition and engine operation is 3 factors. For engine condition, gear state is 6 factors. For engine operation, gear state is 6 factors. And direction is 3 factors. Now, so therefore, total number of states is 6 into 6 into 3, that equal to 108 states. A car with a broken transmission does not move for long, thereby further decreasing the number of states. So whenever it's going to be broken, what happened? It comes to reducing about the number of states. Whenever a broken engine, a broken part, okay, etc. So it's going to reduce about the number of states. Okay. Third one, equivalent states. What is meant by equivalent states? If 2 states takes different sequence of inputs, and produce exactly same sequence of outputs. What is the point here? If two states takes different sequence of inputs and produce exactly the same sequence of output, then the two states are called equivalent states. For example, S is one state, A is one state, B is one state, C is one state. Now S to A is nothing but the input A. S to B is nothing but input B. Now S to A is taken one input A, then S to B is taken one input B. That is total different. But it's going to be obtained about the same sequence of outputs in C here. So in this case, these two states A and B is called as a equivalent states, and it can be shown like this. Can be shown in this. Now next one. In the above figure, let us assume that the system is in state S. From S, an input A changes to state A, and input B changes to state B. Okay, that means S to A is A, S to B is B. If the states A comma B takes different sequence of inputs, this and produce exactly the same sequence of output side, then we say that these two states A, B are equivalent states. Now the state graph can be minimized by combining these two equivalent states as shown in the following figure. So the above state graph, this state graph can be combined or can be minimized by combining these equivalent states as shown in the following figure. It comes like this. So A comma B, two states can take the input A comma B and it obtain about the output at C, same output. Equivalent states can be recognized by the following ways. Let us consider the following example. One is one state, A is one state, B is one state, H is one state, C is one state. From 1 to A, the input is A. From 1 to B, the input is B. At A, input is D, output is Y. So from A to H, input is E, output is Y. At B, input is D, output is Y. From B to C, input is E, output is X. From A to C, input is E, output is X. From B to H, input is E, output is Y. Now here, except AB inputs, the system behavior in two states AB are identical for every input sequence. Yes or no? Except AB input sequence, the remaining inputs are same. See here, from A to H E, then B to C is E, then B to H is E, then A to C is E. So all inputs are same. Okay. So let us consider the following equivalent states. In these equivalent states, so from 1 to A1, so the input is A. From 1 to B1, the input is B. From A1 to A2, input is B. B1 to B2, input is B. From B3 to A2, input is B. From A3 to B2, input is B. From A2 to B2, input is A. From B2 to A2, input is A. From B3 to B3, input is A. From A3 to A3, input is A. In this case, what happened? Here A1, B1 are equivalent states. Here, which one is equivalent states? A1, B1, both are equivalent states because at the top it is A by Y, at the bottom it is A by Y. Okay, equivalent states because it takes different inputs A, B, but produces same output U. So it takes different inputs A, B, but produces same output U. See here U and U. Okay, that's why A1, B1, both we can call as equivalent states. The state table to the above figure. State table, write the state table. From 1 to A1, what is there? A input, U output. So what are the different states? First we write the states. What are the different states here? 1, A1, B1, A2, B2, A3, B3. These are the different states. What are the different states here? 1, A1, B1, A2, B2, A3, B3. That's why written here 1, A1, B1, A2, B2, A3, B3. Now input and input. So here what are the different inputs and outputs? First, in state, what are the two different inputs? The two different inputs are, one is nothing but, second one is AB. That is two different inputs. A is one input, B is one input. Now you go to the what is 1 to A1 is Y. 1 to A1 is Y. See, 1 to A1 is Y. 1 to A1 is 1. From 1 to, see here, clearly see 1 here, state 1 to A1 is Y. 1 to B1 is U. 1 to A1 is Y. From 1 to A1, output is Y. Output is Y. A1 to A1, output is Y. A1 to A1, output is Y. Here A1 to A1, output is Y. A1 to A1, output is Y. A1 to A1, output is Y. Here it is actually 1 to A1 is U, not it is Y. You just correct U. Similarly, for 1 to B is 1 to B1 is, what is the value? 1 to B1. From 1 to B1 is U. 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 So 1 to B1 is U. It is correct. Now come to the A1 to A1 is Y. A1 to A2 is X. A1 to A2 is Y. A1 to A2 is Y. Then A1 to A2 is X. A1 to A2 is A1 to A2 is A1 to A1 is Y. A1 to A1 is Y. Then A1 to A2 is X. A1 to A2 is X. A1 to A2 is X. Okay. So A1 to A2 is X. Similarly, B1 to B1 is Y. B1 to B2 is X. Similarly, A2 to B2 is W. A2 to A3 is U. Similarly, B2 to A2. B2 to A2. See here, B2 to A2 is W. B2 to B3. B2 A2. B2 A2 is W. B2 A2 is W. Okay. Then B2 to B3 is U. B2 to B3 is U. B2 to B3 is U. So like that we can write about what are the different inputs. Again I am repeating. So first one, 1 to A1 is U, but here it is wrongly typed. Then 1 to B1 is U. A1 to A1 is Y. A1 to A2 is X. B1 to B1 is Y, X, Y. Then B1 to B2 is X. A2 to B2 is W. A2 to A3 is U. B2 to A2 is W. B2 to B3 is U. A3 to A3 is U. A3 to B2 is Y. B3 to B3 is U, and B3 to A2 is Y. So from this figure it's going to be obtained. Okay, from 1 to A1 is U, 1 to B1 is U, then A1 to A1 is Y, B1 to B1 is Y, like that. Okay, so by seeing this figure, you can obtain. By seeing this figure, we can obtain about this state table. So previously obtaining about this from this state graph, we can obtain about the following state table. Now the merged equivalent states, you merge it. Then what happened? From 1 to A1, there are two input values, A comma B, but output values are U only. From A1 to A1, the output is Y. From A1 to A2, the output is X. From A2 to A2, output is W. From A2 to A3, output is U. From A3 to A2, output is Y. Then from A3 to A3, output is U. So we can find about the above merged equivalent states. But here, previously all are uniform. See here, uniform. If you take a center line and merge it, same. If you take a line, center line like this, merge it, same. Okay, merge it or not merge it, just bend it, same. So if you take a center line, see the top side and bottom side all are same. Okay, in directions and also its states. That's why they called as a equivalent states. But you come here, in this case, if you take a center line, so from the center line to here there is an arrow, but from center line to in this side there is no arrow. So not both are same. Okay, so therefore it is called as a unmergeable states. So this is called as a unmergeable states. So here only I'm taking about B3 to A2 is input is B and output is Y. Remaining this one. Here 1 to A1, 1 to A2. Inputs are A, B and outputs are U. From A1 to A1, X. From A1 to A2, output is X. From B1 to B2, output is X. From A2 to A2, output is W. From B2 to B2, output is W. From A2 to A3, output is U. From A3 to A3, output is U. From B2 to B3, output is U. From B2 to B3, output is U. B3 to B3, output is U. Then B3 to A2, output is Y. So these not merged states. This is called as a unmergeable states. This is called as a unmergeable states. Unmergeable states. Then transition bugs. What is meant by transition bugs? Changing from one state to another state is called transition. What is the definition of transition? Changing from one state to another state is called transition. So the bug in transition is called transition bug. The bug in transition is called transition bug. First one, unspecified and contradictory transitions. What is meant by unspecified and contradictory transitions? If a transition may occur between states, but the transition is not specified, remember, if a transition may occur between states, okay, but that transition is not specified, then the transition bug occurs. And the transition is called unspecified transition. If a transition is not possible, but then there is a method used. If transition is not possible, then there is a method used. Method is used. If there is no such method available, then that input becomes inefficient. To avoid transition bug, one transition must be specified for every input. Remember, to avoid transition bug, one transition must be specified for every input and state combination, input and state combination. A program does not contain contradictions if one input must be processed at a time to produce desired output. This point is very important. A program does not contain contradictions. Okay, there is a program. That program does not contain contradictions if one input must be processed at a time to produce desired output. If one input must be processed at a time one input must be processed to produce the output. If a transition does not possible between states, but the transition is specified. Here, what we can say, if a transition does not possible between states, but that transition is specified, then the transition bug occurs, and that transition is called contradictory transition, and that transition is called contradictory transition. That is, if a programmer does not take all the measures of a program, that is, if a programmer does not take all the measures of a program, then contradictory transitions may occur. If a programmer does not take all the measures of a program, then contradictory transition may occur because transition may not be possible between some of the states. For example, if a single bit of a state is misplaced by the programmer, then it doubles the number of states and contradictory transitions may occur. So what we can say here, if a single bit of state is misplaced, okay, you are not put. So in that case, what happened? The programmer, then it doubles the number of states and contradictory transitions may be occurred. Then second one, unreachable states. Next one is unreachable states. The unreachable state is like unreachable code. We know all of you. We know about what is meant by unreachable code. So the unreachable state is like a unreachable code. If a transition is not specified between two states, then that states are unreachable. That means we are not able to specify transition. That means we can't reach about to other state. If any incorrect transition occurs, if at this time, if any incorrect transition occurs, then the state becomes unreachable. Unreachable. Next, dead states. A dead state is a state that once entered cannot be left. What is meant by dead state? A dead state is a state that once entered, it cannot be left. In programming, set of states may be dead state because a program has two stages. In the first stage, an initialization process takes place that consists of number of states to be initialized. In second stage, set of functional states takes place in which operations of the states cannot be completed. So the functional state becomes dead states. So dead states you can say by two ways. The dead states are, you can say by two ways. One is initialization process takes place that consists of number of states to be initialized. Okay. But in second stage, now set of functional states takes place in which operations of the states cannot be completed. That means functional state becomes dead states. Functional state becomes dead states. Okay. Now, the only solution to this problem is restarting the system. Restarting the system. Third one is output bugs or output errors. The errors in output are called output errors. The states, the transitions, and the inputs may be correct. Remember, the states is correct, the transition is correct, and the input is correct, and there may be no dead or unreachable states. But the output for the transition may be incorrect. That is a problem in case of output bugs. Output for the transition may be incorrect. So here output bugs comes under the transition. Outputs must be verified. Outputs must be verified independently. Outputs must be verified independently for states and for transitions. States and for transitions. Okay. Outputs must be verified. So the errors in input output are called output errors. The states, the transitions, and the inputs may be correct, and there may be no dead or unreachable states, but the output for the transition may be incorrect. So because of that reasons, we are getting about the output bugs. Outputs must be verified independently. Outputs must be verified independently for states and for transitions. Okay, thank you. Partitioning algorithm. Next question is partitioning. What is meant by partitioning algorithm? It is an algorithm which is used to transform the graphs with loops into loop-free graphs. It is an algorithm which is used to transform the graphs with loops into loop-free graphs. There are certain points to remember here. They are: a graph is loop-free at the top level. A graph is loop-free. A graph is loop-free at the top level. Many graphs with loops are easy to analyze. Many graphs with loops are easy to analyze if you know where to break the loops. If you know where to break the loops. The algorithm is used to develop a tool. This algorithm is used to develop a tool which can identify the loops. The partitioning algorithm represents a plus a whole power n hash, a plus a whole power n transpose. Example: consider the following flow graph and its graph matrix A plus I and its graph matrix A plus I. See here, this is a graph. Here you can consider all are 1. 1 to 2 is 1, 2 to 7 is 1, 7 to 2 is 1, 2 to 3 is 1, 3 to 4 is 1, 4 to 6 is 1. Then 7 to 3 is 1, then 5 to 3 is 1, 4 to 5 is 1, 3 to 4 is 1, 8 to 3 is 1, 4 to 6 is 1. So you can place it here. So, and its I matrix means all principal diagonal matrix you can enter 1. Okay. Then all principal A plus I means all principal diagonal you can enter 1. So here it is 1 to 2 is 1 already, 1 to 1 is 1 principal diagonal, 1 to 2 is 1 already entered. then from 2 2 to 3 is 1, 2 to 3 is 1, and 2 to 7 is 1. From 3 3 to 4 is 1. From 3 to 4 is 1. That's all. From 4 4 to 5 and 4 to 8 is 1. 4 to 5 and 4 to 8 is 1. From 5 to 3 from 5 to 3 is 1. From 6 nothing. From 7 to 2 is 1. 7 to 2 is 1. Reverse direction, 7 to 2 is 1. Then 7 to 3 is 1. 2 is 1, 7 to 3 is 1. From 8 to 3 is 1. Okay. Now the transitive closure matrix A plus I whole power n can be obtained by using the following steps. How you can obtain A plus I whole power n means, first step 1, mark all diagonal entries by 1. Mark all diagonal entries by 1. Step 2, the flow from node 1 to node 6 is node 1 to node 6. What is the flow? 1 to 2, then 2 to 7, then 7 to 2, then 7 to 3, 7 to 2, then 2 to 3, then 3 to 4, then 4 to 5, then 5 to 3, then 3 to 4, then 4 to 6. Similarly, from step 3, so mark nodes 1, 2, 3, 4, 5, 6, 7 by 1. Step 3, the flow from node 2 to node 6 is given by 2 to 7, 7 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 3, and 4 to 6. So mark the nodes 2, 3, 4, 5, 6 by 1 in second row. The flow from node 3 to node 6 is 3 to 4, from 3 to 4, 3 to 4, 4 to 5, 5 to 3, 3 to 4, 4 to 6, 4 to 6, 3 to 4, 4 to 5, 5 to 3, 3 to 4, 4 to 6. So mark the nodes 3, 4, 5, 1 by 1, by 1, by 1, by 1 in the third row. Next, the flow from node 4 to node 6, 4 to 5, 5 to 3, 3 to 4, 4 to 6. So mark the nodes 3, 4, 5, 6 by 1 in fourth row. Step 6, the flow from node 8 to node 6, node 8 to node 6. The flow from node 8 to node 6 is 83, 8 to 3, 3 to 4, 4 to 5, 5 to 3, 3 to 4, 4 to 6. That means here from 7 is over, from 8 to 3, 3 to 4, 4 to 5, 5 to 3, 3 to 4, 4 to 6. So mark the nodes 3, 4, 5, 6, 8 by 1 in the 8th row. Therefore, the transitive closure matrix is it is obtained A plus I whole power n equal to mark, because in first row you can mark 1, 2, 3, 4, 5, 6, 7. In second row you can mark 2, 3, 4, 5, 6, 7. In third row you can mark 3, 4, 5, 6. Fourth row you can mark 3, 4, 5, 6, 3, 4, 5, 6, 6 to 6 only, 1, nothing, 6 to 6, nothing. 6 is not there, 7 you can mark this, and 8 you can mark this. Now you write about the A plus I whole power n transpose. A plus I whole power n transpose. That means, so the rows you can write into columns, the rows into write into columns. So the rows into write into columns means the row values 1, 2, 3, 4, 5, 6, 7, 1. You enter into columns 1, 2, 3, 4, 5, 6, 7. Then second 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7 you can mark vertically. Then next the horizontal 3, 4, 5, 6 mark it into vertical. Then horizontal 4, 5, 6 you mark it 3, 4, 5, 6 you mark it vertical. 3, 4, 5, 6 you mark it vertical. 66 is 1. Then from 2 to 7 you can mark it vertical. From 8 to 8 you can mark it vertical. Now you have to write about the intersection of transitive closure matrix A plus I whole power n and transpose matrix A plus n is given by identifying similar rows and column entries from A plus I whole power n and A plus I whole power n t. Similar rows and column entries. Similar rows and column entries. A plus I whole power n hash A plus I whole power nt means similar rows and column entries. That means you see here it is 1 to 1 is there, here 1 to 1 is there. So you can mark it. Here it is 2 to 1, here it is not there. So 2 to 1 don't mark it. 2 to 1 don't mark it. But 2 to 2, if you see here 2 to 2 mark entry is there, 2 to 2 mark entry is there. So you mark here 2 to 2 as 1. From 3. So from 3 to 3 mark entry is there. 3 to 1, 3 to 2 is not there here. 3 to 3 is only there, 3 to 3. So then 3 to 4 it is there. 3 to 5 it is there. So like that here you write 3, 4, 5 is 1. Similarly from 4 you can entry. Similarly from 5 you can entry. Similarly from 6 to 6 1 is there, 6 to 6 1 is there, you can entry. In 7 from 7 so 7 to 2 it is there, 7 to 2 it is there. 7 to 3 is not there, but 7 to 7 it is there. 7 to 2 it is there, and 7 to 7 it is there. 7 to 2 and 7 to 7. 7 to 2 and 7 to 7 is there. So from 8th only 8 to 8 last entry it is there. Remaining here it is not there. So here it is there, but here it is not there. So only from 8 to 8 it is there. So this gives about the A plus I whole power n hash A plus I whole power n transpose. From the above matrix, by comparing a row column with other row columns, the equivalent nodes to be grouped. After grouping A equal to 1, B equal to 7, A equal to 1, B equal to 2 and 7, B equal to 2 and 7, C equal to 3, 4, 5, D equal to 3, 4, 5, C equal to 3, 4, 5, D equal to 3, 4, 5 is same. 3, 4, 5 is same here. 3 entries don't take. Then next sixth one, D equal to 6 and E equal to. Then next here it is 7. Already 2 7 entry is there. Here 7 2 entry is there. Here again here 2 7 entry is there. 2 7 entry is there. Don't take that. And last 8 8 is 1. That means what we are taking here means the equivalent nodes to be grouped. So by comparing, already entry is there. Don't take. Okay, already entry is there. Don't take. Already entry is not there. Take. So A equal to 1, B equal to 7, C equal to 3 4 5, B equal to 6, C equal to 8. The graph and graph matrix representation to the above these values are given by like this. Okay, so one it is there, 1 is nothing but A, B 2 7 is there, 2 7 is there, B, then C, next is C 3 4 5 is there, C 3 4 D6 E8. So D6 E8 you can view like this. So from this you can write about the graph matrix. So the graph matrix is nothing but A2 from diagonal, principal diagonal you put 1, then A to B is 1, A to B is 1, then B to B is B to C is 1, B to C is 1, then C to D is 1, C to D is 1, then E to C is 1, and E to C is 1, and E to E, that is principal diagonal, is 1. So and place the entry here. Relation and different properties of relations. So here we will see about the relations and different properties of relations. Relations and different properties of relations. So what is meant by relation? First question is what is meant by relation? What is meant by relation? The property by which two nodes are interconnected. The property by which two nodes are interconnected is called a relation. What is meant by relation? The property by which two nodes are connected. How two nodes are connected is called a relation. A relation can be represented by a link. with connecting nodes, because here it is two nodes are interconnected means what is the relation? There is nothing but a link with connecting nodes. A link represented with link weight. Link means always represented by link weight with small letters. This link weight can be numerical, logical, illogical, or whatever may be. Okay, this link weight may be numerical, logical, illogical, or whatever. The graph matrix, which consists of unweighted simple links, is called a connection matrix. The graph matrix, which consists of unweighted simple links, that is unweighted, so no weight, simple links, is called a connection matrix. The graph matrix, which consists of a weighted simple links, is called a relation matrix. Relation means it is nothing but the weighted simple links. Weighted simple links. Unweighted simple links means it is called as a connection matrix. Now, different properties of relations. What are the different properties of relations? The different properties of relations are, first one is transitive relation. Transitive relation. What is meant by transitive relation? A relation R is transitive if A or B and B or C, then A or C. That is, A relation to B, B relation to C, then A relation to C is called as a transitive relation. Is called as a transitive relation. Examples of transitive relation is connected to, is greater than or equal to, is less than or equal to, is a relative of, etc. Examples of intransitive relations are is a friend of, is a neighbor of. That means if you want transitive relation, then you can take is connected to, is greater than or equal to, is less than or equal to, is a relative of, etc. In intransitive relation, there is no transitive relation. At that time, you can take is a friend of, is a neighbor of, etc. Then second one, reflexive relations. A relation R is reflexive if for every A related to A relation to A, then it is called as a reflexive relation. This relation represents a self loop, because ARA means what is ARA? It is nothing but a self loop. It is nothing but a self loop. This relation represents a self loop at every node. Examples of reflexive relations are equals, is a relative of, etc. Examples of irreflexive relations include not equals, is a friend of, etc. Is a friend of, etc. Third one is symmetric relation. What is meant by symmetric relation? A relation R is symmetric if A or B, then B or A. A or B, A relation to B, then B related to A. This relation represents if a link from A to B, then there is also a link from B to A. Okay, a graph whose relations are symmetric is called an undirected graph. A graph whose relations are symmetric is called an undirected graph, and a graph whose relations are not symmetric is called a directed graph. So a graph whose relations are symmetric, then it is called undirected graph, and a graph whose relations are not symmetric, then it is called a directed graph. Examples of symmetric relations are a relative of, is brother of, etc. Then next, examples of asymmetric relations are are the boss of, is greater than, etc. Next one is anti-symmetric relations. A relation R is anti-symmetric if A or B and B are A or B, A relation to B and B relation to A, then A equal to B. Then it is called as a anti-symmetric relation. Examples of anti-symmetric relations are is greater than or equal to, is a subset of, etc. Examples of non-anti-symmetric relations are is connected to, is a relative of, etc. Is connected to, is connected to, is a relative of, etc. Is a relative of, etc. Next, second one, equivalence relations and partial order relations. Equivalence relations and partial order relations. What is meant by equivalence relation? A relation is said to be an equivalence relation if it satisfies transitive relation, reflexive relation, and symmetric relation. That means transitive property, reflexive property, and symmetric property. So a relation is said to be an equivalence relation if it satisfies transitive, reflexive, and symmetric properties. If a set of objects satisfy an equivalence relation, If a set of objects satisfy an equivalence relation, then it forms an equivalence class. Okay. The idea behind a partition testing is that we can partition the input space into equivalence classes. So the idea behind a partition testing. So if you consider about a partition testing, then we can partition the input space into equivalence classes. Okay. Then partial ordering relations. A partial ordering relation satisfies the reflexive property, transitive property, and antisymmetric property. A partial ordering relation satisfies the reflexive property, transitive property, and antisymmetric property. A graph which shows partial ordering relation between its nodes is said to be partial ordered graph. So a graph which shows partial ordering relation between its nodes is said to be partial ordered graph. Partial ordered graphs have different properties. They are loop free. First one is loop free. Second one is there is at least one maximum element. There is at least one minimum element. If you reverse all the arrows, the resultant graph is also partial ordered. If you reverse all the arrows, the resultant graph is also partial ordered. The maximum element A represents the relation X or A. Similarly, the minimum element A represents a relation A or X. So here, the maximum element A represents the relation X or A. Similarly, the minimum element A represents a relation A or X. Examples are trees and loop-free graphs.